Well, I wanted to get into the design features. We're not going to go into the design rationale. That'll take a little too much time. But over the next few talks, you'll get the impression of what the design rationale is. But I think it's important that you understand the design features that we're trying to strive for. And again, I want to acknowledge John Kagi was the first one that heard me talk about this idea, and then Lou Kepler. And Lou's comment to me was, "Are you crazy?" But he's as crazy as I am because he's been working with us on this. And here's some examples of the neck sparing stem or neck stabilized stem. And it was really Mike Freeman, while Peppino was doing his work, it was Freeman that really made the argument for saving the neck. And certainly we're going to hear Declan talk more about the bending moment and the torsional moment. But when you retain the neck, you change the resistance, and you can withstand more torque, and you can also withstand more bending. And so we're going to hear more about that. There is increased risk associated with mechanical impingement, and we have to appreciate and understand the limitations of the technique and the design. But certainly you can see the little slide up at the top, and this is certainly what some companies and some doctors are doing in the way of customs. Now, I think that would scare all of us, the amount of offset with that type of device. And we do indeed see both modular devices and monoblock devices that have increased offsets of fracture, and we're also seeing, as Dave pointed out, an increase in periprosthetic fractures. So again, why save the neck? And again, it's Freeman who really made this argument, and it's reducing the bending moment and the torsional moment. And one of the things we've seen over the last few years is there's an increased tendency to increase offset. We know we get a better functioning hip on that, and offset is sometimes underappreciated how much torque increases at the stem bone interface by increasing offset, and retention of the neck reduces the loads at that interface. We also wanted to, I've been around long enough to be through the hip resurfacing, and we wanted to see something that was a little more tissue friendly. And here's an example of John, and he's going to talk more about hip resurfacing. But here's his approach doing a neck sparing device. So we think it is a little more conserving on soft tissue. And again, we know from Peppino's work, we provide better supply if we save the neck. There's more axial and torsional stability, as proven back in the 80s by Leo Whiteside. There's also, in today's environment, just more tissue to work with, and potential for less blood loss, and for potential for a quicker rehab. Now, we still have to prove some of this, but let's recognize the issues associated with neck retention. Mechanical impingement is the biggest concern, and we've seen a lot about that. And so head-neck ratio, and we think we have a design that is predictable, and we have not seen any mechanical impingement problems, and Peppino hasn't reported any mechanical impingement problems, but it is something that the surgeons will talk more about in the technique on how to assess that. Surgical difficulty, certainly retaining of the neck, I think particularly in the anterior approach, might require some more posterior releases. John will address that. Implant stability is very impressive. That's the one comment everybody has made, is that this stem is very stable initially. And the advantage of conversion or revision, you have got more tissue and bone to work with. Survivorship, Peppino is the world's expert in this area. He's had great results for aseptic loosening. He's had disappointing results for bone remodeling, so we think we've come up with a little different model. And here's what we're talking about. Here's a Peppino stem, which has just been an excellent device. He originally worked in the biodynamic, which was chrome cobalt, had disappointing bone remodeling, and has since gone to titanium. Again, he's had very predictable results from pain and function, but he's still seeing some bone remodeling. These are the devices we're going to be talking about, with the emphasis on this one. It's the ARC stem here in the US, and we're also seeing some work with Corin, and these are the curved neck stabilized stems versus tapered or straight stems. The curve historically comes out of the Thompson prosthesis, and everybody thinks that the old banana stem was wrong. The application might have been wrong, but the curve was right on target, and the curve is almost identical to what Mueller and Thompson did, and certainly the application has changed over the years. this is a curved stem, and people think that that's simple, but it's a different animal. And Del Schutte did some nice work on cadavers looking at offset, and you really got to have about 15, 20 degrees of internal rotation to be able to measure your offset and also get a true medial arc. And if you can't get your patient to internally rotate, do the contralateral side. But we're really trying to shape this bone. So we're going back to a rasping technique as opposed to a broaching technique so we can shape the medial curve. The other advantage here is that we keep the cortical ring intact, and Peppino makes a big deal about keeping that cortical tension band in effect. It also provides a physical barrier for migration of particulate debris, and so we think there's a significant advantage to that. And here's Peppino's current CFP stem. And again, it's functioned very, very well, but he is seeing some significant stress shielding. Has it been a problem to date? No. But again, if we're going to design something, we want to try and design and improve around it. So we've come up with a little conical flare idea that offloads hoop into compression a little quicker. And our x-rays at 2.5 years are confirming our FEA modeling, and Declan's going to talk a little bit more about some FEA modeling. And this is conical flare came out of some work I did back in the early 90s with kind of an SROM with a conical collar, and that really has maintained the load here. And so we kind of worked around that concept, came up with a curved stem design with a conical flare that is designed to, again, offload compression and maintain the medial calcar. The stem is a curved stem. It kind of a trapezoidal curved stem. It has a T-back for increased surface contact and more torsional stability. It is porous spray coated with HA, and it's 0.5 millimeter per side. The T-back is about 1 millimeter per side. So we're getting a little bit of maybe a too much press fit on the smaller profile patients right in this area. But we also have a sagittal slot, and I do want to acknowledge and recognize one of my friends, Jim Henry, who actually contributed to this concept, and it actually is an excellent design. You'll see some examples where that really functions. Short curved stems don't seem as sensitive to stem position as standard cementless or cemented stems. We can be in slight varus, neutral, or valgus, and it doesn't seem to affect either the bone remodeling or the function. And actually, there might be a little advantage if you think your stem is going to be too small, put a little bit of valgus into it, and you actually can wedge it in there. And if you want to load a little bit more on the medial calcar, you can put it in the varus. But right now, we haven't seen any differential on stem positioning. The distal tip, this is a key factor. We recognize that curved stems could possibly be positioned in the varus. So we angled this at 11 degrees. So if you do get slight varus, we don't have any end stem contact. And I think that's been a very significant design feature, along with the sagittal slot, where back with the SROM, we had designed a coronal slot. The sagittal slot is reducing bending stiffness, and we didn't want any load transfer down there. And here's what we're seeing here. And with solid stems, you know, you have a tendency that you can get distal spiral cracks. We've not seen that with this design at all. We've seen it with Peppino's. So that was one of the motivations for the sagittal slot. And again, this little angled tip allows us to, if the stem's slightly malpositioned, not to have end stem contact. There are currently 5 stem sizes. It's a very simple system. We are probably addressing 90% of the indication. We felt initially it would be at 80%. We definitely need to go to one size down and possibly one size up, but it's a very simple, straightforward system to work with. We do have a modular neck, and you know, I've been an advocate of modularity for a long time. The difference here is we have a chrome cobalt modular neck, and the neck sparing feature reduces the stress placed on that modular junction. We insisted right from the beginning it'd be chrome cobalt. We have neutral, varus, valgus, and shortly introducing an anteverted neck. And it allows you to fine-tune your joint mechanics. Also, it gives you an opportunity to do the stem first, which Dr. Kepler will talk about. Bearing material. We wanted to make sure that the surgeon could pick the bearing material. We use a 12-14 Euro taper, a specific standard from Ceramtech. and so that the surgeon can pick ceramic, metal, polyethylene. We don't want to be in the position to dictate. We want you to be able to pick. And we are starting to see some nice indications for this dual mobility cup in small female profiles. And again, surgeon picks the bearing material. We wanted something simple, reproducible. And here's an example, anterior approach, John Kage, who uses no special instruments, Charlie Bryant, who uses the OmniTrack hook, and Brad Rederick and Tom Tkach use the arch table, and we have found it to be reproducible. And in the posterior approach, Harry Rubash came in to visit us in Cleveland with Lou and Brad Vaughn, Ed McPherson. We've done some anterolateral approaches, so we think the system is user-friendly, and this is the concept. Only time will tell, and at this point, I'd like to ask Declan Brazil from Australia to come up and give us some basic science. Thank you.